Now, so section 10 point, where are we going? Oh, nope, way beyond. Here we go. How could you have done this problem? But what would have been the worst way to do this problem? The way that poor little Hannah was trying undo to do it and told you guys that homework was awful and horrendous and everyone should cry. Because the Taylor polynomial formula says, in order to get a Taylor polynomial, which the first, oh dear, that's not what I want. Lo siento, everybody. What? Sorry. Yes. I was saying Taylor. Remember, all Maclarens are Taylors. Taylor's centered at 0. But thank you, Justin. I appreciate that. I should say Maclaren. To get a Maclaren polynomial, the first 4 non-zero terms, we're not exactly sure. I'm just going to put an n for right now, because sometimes it gets a little confusing as to, like, 4th degree? No, it didn't say 4th degree. It just said the first 4 non-zero terms. We'll figure out what the degree is in a second. But in general, don't we need G prime, because it's a G? No. How does a Taylor or Maclaren, either one, how do they both start? G of, exactly, G of, not a G prime. Think of linearization with the f of move to the other side. So f of a plus f prime of x minus a. In this case, G of a, well, wait a minute, where are we centering it at? Maclaren is at 0, so we can say G of 0 plus G prime of 0 times x minus 0 plus, where do we go after the whole linearization thing? F of a plus f prime of x minus a, that's what we have so far. Then what? Don't forget your, I tend to forget the factorial all the time. And then we're just going to do dot, 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 because some of these might go to 0, and they say the first 4 non-zero, so maybe one more is enough, maybe not. We'll check it out. But as, did you get it in? Okay, so if you need to plug in 0 to g, is it that big a deal? Nah, 0 times cosine of 0 is 1, 0 times 1 is 1. Ha, got it. But now when does it get hard? You need g prime of, oh, we have to take a derivative, and it's a product rule. And oh no, we're going to take another derivative of, after a product rule, another product rule. Oh, probably an addition of product rules. And then a third derivative, oh no, of 3 product rules. And how could this get awful? If we worked with this function from the very beginning. What's the alternative? Cheating. And not working with this function from the beginning, but instead thinking of someone else like, let's use h. And h is cosine. And so we could say, let's just work with cosine. And let's just kind of table that for a bit. Is there a special Maclaren according to what I showed you in the Google Classroom for cosine? Yes. It is going to be an Endeavor card. Yes, it is. Your notes, no, your book mentioned something about a table. We might actually add a couple on. But for right now, is there a special one for cosine? Yes. Have we seen the one for sine? Yes. How do we remember sine versus cosine? Sine has what powers of x? Cosine, odd symmetry, even symmetry. Wait, it's not even, that's a 1. X to the 0. 0, 2, 4, 6. Got him, right? So we can say 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc., etc., etc. So let's come back and let's say, okay, instead of doing this whole Taylor, Maclaren, polynomial building thing, let's just say we know cosine, because we do, right? Or you would have, or you will, once you learn those special series, right? So we could say equals, just cosine, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. See why I didn't put an n? The first 4 non-zero terms don't exactly go like 0 degree, 1st degree, 2nd degree, 3rd degree, 4th degree. So I didn't exactly know what the nth degree was. But also, this is not my function. That's just h. Yeah.
Can I ask you a question?
Yeah.
It's like in the homework last time it said like find the 3rd order, and then other times it would say find the 3rd degree, and it would be like different answers. Like one would actually be like go till you find like x to the 3rd, and the other times it would be like go to the 3rd order, and it would just be like
The first 3?
yeah. And I was confused.
Whenever it says degree, no, that's part of the struggle of these types of problems. If it says to the degree, it specifically means the power of the x term. It specifically means the power of the x term. If it's talking about order, this goes back to like the orders of differential equations, first order, second order, third order, which is first derivative, second derivative, third order. Off the top of my head, I would say the number of the derivative. But then that should have been landing about the same place as the degree. Except in special cases where you plug in like an x squared, like the whiteboard example, which would get you to a 10th degree instead of a 5th degree. We'll have to look at it when we go over homework questions and then clarify. Yeah. Maybe order doesn't mean as simply as I thought. But in this case, at least it was very clear. It said the first 4 terms, so it wasn't either of the wordings. But thanks, Maggie. That is where some of these get weird. Hold on. We're not done because this is h. But how are we going to make g from h? The nice thing is, since we've made cosine into a polynomial, we can multiply x by cosine by multiplying x by the polynomial. Yeah. Which saves us from all of our crazy product rule derivatives. Oh, I did not mean to change the factorials. Thank you, guys. I'm too used to Taylor polynomials where you have the degree and the factorial matching. First 4 terms, dun, 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 dun. Guess what would have happened if we had taken the first, second, third, fourth, fifth, sixth, 7th? We would have had to take 7 derivatives. We would have had to take 7 derivatives because all the other ones would have been 0. We would have matched up with this eventually. But 7 derivatives of a product rule? Anybody say heck to the no? Yeah. No. Right? So, what was I trying to show you at the very end of yesterday? Could you, in something like letter C, could you, and would it work to build the Maclaurin polynomial, because it said centered at 0. Oh, it just said Maclaurin. Could you do 4e to the u times u prime for g prime? And then have a product rule and do the product rule for g double prime, and then do the product rule, the addition of the product rules for the next one? Yes. Or special Maclaurin for e to the x. Could you start with h of x equals e to the x? Now, hold on. Ooh. Dilemma. What did I just put in between cosine and this? Equals. But do I have infinitely many terms? Woo! The equals is okay now. But was it okay here? Equals and approximate, think Eulers and how important that equals and approximate is. Or tangent line approximation, like ln of 1.1 versus a tangent line approximation. This is only, remember when we were watching, I saw this in your book the other day. They went through, remember how I had you graph sine? Okay. If you only have so many terms, which each one, oh, that was so much easier. Why didn't I think of that? Do you guys see how they built it in their calculator? They did y1 plus the next term, and then y2 has this plus the next term, and then the next one could be y3 plus the next term, and then y4 plus the next term. That was so much better than us. Anyway, if you only have so many terms, Maggie, it only converges for a certain amount of time. So we can't say equals because it doesn't. It equals for a little bit, but not forever, unless you keep on, keep on keeping on.
What if they specifically ask for 4?
But then I shouldn't have written cosine equals, and I shouldn't write x cosine equals. What I could do instead is take this shabam, It's all about notation, and I could do the polynomial equals. The polynomial equals that. True, the 7th degree Taylor Maclaurin, or Taylor centered at 0, sorry, Justin. The 7th degree polynomial equals that, but does that function equal that? No, it's an approximate. Or at least it only converges for a certain interval. Sorry about my notation, guys. I apologize. But is there a special Maclaurin for e to the x? Yeah, I could say e to the x is equal to. Do we need to write down this endeavor card? Yep. Pause. You get it, right? We need this. We need this. Oh my goodness, we need this. Endeavor number? Gracias. I'm going to go ahead and look in your book, though, because they said that there was a table, and they have their own. This is one that I got from Mr. Calculus in a seminar from, I don't know, a few years ago. I think it was my first year teaching BC. As far as this specific, he said this is all you needed to know. Our book does throw in some good ones, though. Hold on. You guys have 1 over 1 minus x, check. E to the x, check. Sine of x, check. Cosine of x, check. Ln of 1 plus x, check. Or x plus 1. Oh. What's wrong? I started teaching CalcBC for, I don't know if you guys know any of those kids, though. Stephen Phillips, Tamara Avila, Zach Stone. It was with Milad and Sina, too, right? Because it was the first year where there were a lot of juniors the year before in AB, and they were like, we want to take BC. Can't you make a class? And I was like, guys, okay, I'll try. And I made a class. 5? 4 or 5?
Wasn't last year your 10?
Yeah.
Teaching AB?
Oh, teaching here. But yeah, I started teaching AB part-time. What? You guys are year 11. But as far as BC, I think you're year 5 or 6. Does that sound about right? Because I think Petito and Layla and all them were my second year. And they're graduating from college. Milad graduated last year? Okay. Yeah. Yeah. Okay, so your book, if we were to look at it, can I just switch real fast? I'll come right back. Your book has... Okay. Your book not only puts the first few terms, but also the general term and also the summation. So that's not bad to have the general term, because you guys realize whenever we talk about sequence and series, all right. Whenever we talk about sequences and series, general terms do come up, and summation notation might come up as well. So our book might give you some extra detail that you guys might want to look at. For my purposes, I just need you to know what the first few terms are. But as far as AP and what they might ask you as far as general terms or getting it into summations, it might be a good idea. All of these you guys have except, wait a minute, why didn't I have you write that one? How are these two related? Can't you plug in a negative x, right? So plugging in a negative x would give you, well, that's still 1. A negative, oh, that one's going to be positive because a negative squared. Oh, next one's going to be negative. So you could write them separately, or you could just say, like, oh, plug in a negative x. But, yeah. Yeah, you can't just do the geoseries, or you can write it out. I think the AP does like to do 1 over 1 plus x, so they were like, maybe it's good to write it. But guys, there's one other one. Check it. What's the one other one that they add? Tangent inverse. Which tangent inverse, wouldn't that be the integral of 1 over 1 plus x squared? And wouldn't 1 over 1 plus x squared be 1 over 1 plus x with an x squared plugged in? So you could actually get this series on your own by integrating 1 over 1 plus x squared by 1 over 1 plus x with x squared plugged in. But you might just want to write tan inverse. So I think I'm going to add tan inverse. I haven't seen it on an AP question before, but this is an AP-ish book. And it is a nice series. Like, okay, yeah, it's a nice one. And they like to use tangent inverse for limits and for graphs and all sorts of stuff anyway, and for improper integrals, etc. So maybe it's a good idea, huh? So why don't you guys just go ahead and add in tan inverse at the end. I might add in 1 over 1 plus x2, depending. But can we go back? Ariane, you can move if you want. I'm sorry, but I'm not trying to torture you. This is in Google Classroom, but I'm adding in the tangent inverse, which is right above your homework. And if you want to add in the 1 over 1 plus x, I might add that in too. But guys, how easy is this one then? E to the x, what is his special Maclaurin?
1 plus x squared over 2 factorial plus x cubed. That was kind of nice.
And why is he so nice? Because the derivative of e to the x is e to the x. So is anything, I hate it when it does that. Is anything changing when you take derivatives? No. Your prime, 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 prime is the exact same, but this isn't what we need. What do we need? Do I have my first 4 terms I can build off of? Yeah. I can go ahead and instead of writing equals, we can write p sub, we'll get back to it in a second. I'm not sure what sub, but let's go ahead and plug and chug. Don't I get to just distribute 4 times 4 times 4 times 4? It's a polynomial. And then I can plug in, yeah, good, good, good. Plug in the x squared. So 4 with no plug-in, it's just 1, would be 4. 4 times plugging in x squared plus 4 x squared squared plus 4x, well, when we plug in our argument to our x's, remember when you raise a power to a power. So what would the next one be? X squared cubed, power to a power u sixth. Power to a power you multiply. But so much easier than building that by deriving. Does that kind of make sense?
These actually like FRQ ones, like you were saying, like black section.
It could be a part of it. Like this would be like an A of a Taylor or Maclaurin.
Okay, so like 1 point, 2 points?
Yeah, yeah, of building. That gets us to section 10.2 homework that I think we were technically supposed to go over homework answers to today, but obviously that's not going to happen. Oh, Maggie, you asked about free response. I'm not sure if this is a homework question or not. I think I gave you at least a few FRQ-ish ones. But here is, 2008, BC number 6. It's not the exact same. A teacher has kind of tailored it. That's funny. Anyway, coming back, has kind of changed it in order to just, I don't know, have it be close but not exact. But do you guys see this FRQ? Where does it start? But do you think you really want to be taking the first, second, third, fourth, fifth derivatives of this? Nope. No, but what can you use? 1 over 1 plus, maybe 1 over 1 plus x is a good one to memorize. We can plug in x squared. Do you see how it says the first 4 non-zero and the general term? I'm liking our book's version of writing these, I think, more and more as I go along. But then it starts talking about convergence. Then it starts talking about the derivative of, isn't that something we saw in homework about taking power series, deriving, integrating? And then, some sort of error bound. Anyway, we have some more things to learn. We have some more things to see. Remember, interval of convergence, we talked about question marks with that as far as, wait, we know alternating series error, but is there any other type of error we need to know? And the answer is yes. That's okay, but we'll talk about why that's okay when we go over homework questions on Thursday, because we're not going over homework questions tomorrow because we're going on a field trip. Homework attempt is still due tomorrow, but we'll go ahead and grade on Thursday. Let me go find what you're talking about, Maggie. I saw IOC in there too. I just forgot where I saw it.
Yeah, it was like number 5.
Oh, 5 through 12.
8 and 11 or whatever. Oh
Yeah.
my gosh, those questions were, I didn't even know they were asking me. And then they were like, and then find the interval of convergence. And I was like, okay.
But now, well, those questions are using what we just practiced at the beginning of class. Does that make sense?
Yeah, like I was able to like write out, like I figured out the, like whatever it was asking me. But then it wanted me to like, I checked the back of the book and they wanted me to write it like a series, like a summation, like form, I guess. And I didn't know I had to do that? So I check the back and forth and check it.
And technically, they just said in a general term, so you didn't actually need to end in a sigma. You just needed to end in a ... after the nth term.
Okay, but I had to put like the end. Like I had to put it.
The general term is the nth term.
And then it's asked for the.
Interval of convergence, that's what I'm looking at.
Yeah, and then I was like, all real numbers. Because I was like, man, you know, whatever number it actually is, technically all real numbers would like count.
Here we go. This is why they were able to ask it. Because in... Hey, distracted ones, any idea what... Oh, Lagrange, is that what we're saying is how to say his name?
Lagrange, right?
It's Lagrange, yeah. Lagrange. You can have fun with that one. There's Maclaurin, and then Lagrange. Anyway, L'Hôpital, I asked James Calvin. So, coming back. Really quickly, there is a place in your homework where it says something about interval of convergence. Man, this is just a better table. I just need to steal this table. Do you guys see where it talks about for what values of x this is good?
Yeah.
This is geo, x between 1 and -1. This is still geo, x between 1 and -1. This is, oh, it's good for all real as long as I ... keep going forever and ever and ever and forever and ever and ever and forever and ever and ever. So when they were asking about interval of convergence, they're saying if you're using these, check out when it converges, when it converges, when it converges. Does that make sense?
Yeah.
So it's not that we've learned any new convergence yet. Instead, it's that they told us for these special series what the convergence is that we can use. Does that make sense? Okay. Sorry, thanks for that question, Maggie. When they say interval of convergence, the reason I keep on coming back is because there's more that we have to learn. But anyway, on those ones, they just stated it for you. Lagrange. Thank you, guys. Lagrange. Error bound. Going back to the Taylor polynomials, do you guys see up here? Our good old friend R, which stands for remainder. Remainder, error, how far off? Ooh, how far off? R, that's coming back to alternating series just a little bit. Except this is not just for alternating series. So we're talking about remainder, aka error. Remainder.
Oh, you kind of clicked on that. That was nice. You say L'Hôpital. Okay.
James, when you go to France, speak French to your French lady.
He speaks better than the local.
This is going to be our approximate. Because it's our nth degree Taylor polynomial. You could also call it P or T. You crazies. Can't take you anywhere.
Oh my god.
P sub n of x, T sub n of x, whether they call it T for Taylor or P for polynomial, either way, it's an approximate. And who's this guy? Actual. Aren't the placements about the same from the alternating series remainder theorem?
Yeah.
You have the remainder, you have the error, you have the approximate minus the actual. It's how far off. Absolute value, I don't care if it's above, I don't care if it's below. When it comes to Lagrange.
No. Is that an actual thing? Like it's gonna be.
The Z is going to be your existence. Just kidding, it's going to be easy, don't worry. Georgie doesn't know anything. So, coming back. What is this notation? Wait. Alternating series remainder theorem, right? Weren't we talking about the n plus first term?
Yes.
A sub n plus 1. What derivative are we talking about? The n plus first. What factorial are we talking about? The n plus first. What power are we talking about? The n plus first. Can we kind of remember this with the n plus first from alternating? Yes. Except, what is this guy? The nth term of a Taylor polynomial. The problem is, who the heck is Z? So down here, who is Z? Who is Z? For an nth degree Taylor polynomial, R sub n, or the error, is given by the n plus first derivative of Z, the absolute value, which is a little bit tricky, over n plus 1 factorial, x minus c, wherever it's centered, could be 0 if it's a Maclaurin, to the n plus first power, and Z is the x value on, oh, stink. The interval x minus c to x plus c. That maximizes, you're welcome, f to the n plus 1 of x.
We're really good at communication. Please tell me when I do that.
Lagrange is, in some ways, shapes, forms, the worst case scenario.
Please say it again, I can hear you.
It's a one-time.
I actually didn't hear it.
It's too late now.
It's okay. You guys were talking over when James Calvin said it, so I missed it. Worst case scenario. Oh, why do I have ads? I don't even know.
I really hope we can hear that in the recording. It's really hard to hear anything in the recording like
As far as out of the mic, ever since I started recording with this. You can probably hear my hacking cough really well. Lagrange, error-bound, endeavor number 27. Now the nice thing is, sometimes they give us clues, like a graph of the m plus first derivative. So say we are doing the 5th degree Taylor polynomial. They give us the 6th derivative graph. So we can look at it and be like, oh, hey, it's maximized there. And we can steal the z. So you're not always solving like optimization by hand for z. Sometimes they're just giving you clues, and you just have to know how to put them all together. But Lagrange is a bit of a beast that we're going to have to tackle on Thursday. What is your goal for tomorrow morning attempting? And I think you're not going to be able to do Lagrange by Thursday.
Isn't this your Friday?
Yeah, what I mean is there really that big of a difference in my mind to having the Google Classroom homework assignment being due tomorrow morning or Thursday morning? Not really. Do you guys want tomorrow night to work on it? Yeah. Okay. Then let me do section 10.2, do Google Classroom, because we're not grading it till Thursday anyway. But don't forget, I'm going to go ahead and make the deadline Thursday morning, because you're not going to have like class time tomorrow to work on it or anything. So you can have tomorrow night and tonight to work on 10.2. Get your Endeavor cards updated. I'm going to go ahead and make a nicer card. I like the book's notation. Guys, the AP does ask for the general term, and that convergence will also be helpful. So as soon as this class ends, I'm going to go ahead and make a